Accepted.
Okay, I guess we can start. Hello, everyone. My name is Beata, and this is Jacek. We are both software engineers at Google in Poland, and we both work, although on different projects, on making our planet-wide computer efficient. Let me tell you what it means in a second. First, I want to acknowledge that some of the solutions that we have at Google make sense only at the large scale that we have. But some things, most of the stuff that we are talking about here in this presentation is applicable even to smaller scale services, and some thoughts and some pitfalls we'll mention should help you to decide what you really want to do with your service. Okay, so what do we mean by making this planet-wide computer efficient? So first of all, we like to talk about all our data centers as one planet-scale computer. And what it means to make it efficient, it really means to reduce cost of operating it, right? So the different dimension of costs we can be interested in is like how many servers, so machines we need there, how many we need to buy, what types, like how much CPU and memory we need, how many data centers we need to build, or what will be the electricity bill, right? Those things are the things that we want to optimize, and we can do it by making every single service, or call it job, efficient, and then having an ecosystem that allows to transfer this efficiency from the service level to the fleet level. So the things that we actually can measure is fleet-wide utilization, right? If half of our machines are doing nothing, then we are just wasting a lot of money. The sum of RAM and CPU of the serving jobs and growth rate. And you probably can notice that those metrics are not perfect. They are only proxies. Really, when we are making decision about like a single service shape, we are making this decision only on that level, not looking like how many data centers we need to build, right? So they are only proxies. And they are also imperfect for the reason that, as inequality metrics, it can be cheated, right? So, for example, it's easy to have high memory utilization, right, for the wrong reasons. And by the way, I forgot to mention at the beginning, please ask questions during the talk. It will be probably better to make sure we cover it's understandable what we are saying. What I mean is we have a lot of material. If you get lost at the beginning, then it's lost. Okay, so we know what is efficiency, and let's talk about how we run a service. So let's run a service in a data centers or Google internal cloud. The code name for that internal is Borg. And so how it really looks like is that you have your binary, and what you need to write is a piece of config that will help you to run this thing on Borg. And you specify the location, binary, and arguments. It can be much, much larger than it. And then you run the command line, and it runs on Borg, right? But there are two important pieces in this config. First of all, there is a number of tasks. We call it size, and you can think about this as a number of replicas of this service. Then we have requirements, RAM and CPU. We call those limits, and think about it as a size of container. So how much memory and CPU will be allocated for this particular service. I will mention already that if we change those limits automatically, those limits can change often, but they also can change without restarting the task. So they can change in flight. Okay, so why do we even need that limit, right? First two reasons are resource isolation, both on machine, so the server level, and in the cluster level. Like so, a service that is trying to go over those limits is treated as misbehaving, can be throttled, and so on. Another aspect is scheduling the job, right? We need to understand on which machine we can put it because there is enough space for this. And also to understand like how this particular service owner, how much they use CPU in memory, for example, in the fleet. Okay. So how would it work if someone wanted to set those limits manually? So on this graph here, you have the dotted line is usage of a service. And we can just for this purpose, we can assume that it's CPU, okay? And then the black, this line is allocation. So someone sets limit first to some number, let's say 20 CPU, right? The service grows. At some point, the limit is less than the usage. So what happens? Something bad happens. Let's call it an outage, right? Like latency increases, whatever. In particular, it can be throttled and so on. So someone notices it, comes to the computer, right? And okay, what I say, I will just double it, right? So they double it, but the story repeats, right? With your usage, you would have to change this very often to actually not cause any outages and also not cause too much waste, right? So it's not like the ideal allocation would just follow the usage ideally, because you do need some slack. But we want to minimize the waste and get rid of those outage events. So we already noticed that doing it manually, and if you wanted to do it efficiently, would be terrible amount of manual work. We don't want that. Also, it may be not worth that manual work, right? Resources have its cost, but also engineering time has its cost. So if someone spent like a month optimizing 1 terabyte of RAM usage, it's probably not worth it. Okay, another question that the service owner has to ask himself, herself, is what should be the shape of the task, right? You can think about it in those terms. You can get the same capacity, computational capacity in terms of CPU and memory, either having a lot of small replicas or just few larger ones, right? So the thing is that the rule of thumb is to prefer larger tasks, but having a smaller number of them. Why? You reduce overhead, right? If you have many tasks doing nothing, they waste more resources than just a few tasks doing nothing. It's easier to do load balancing. It's less volatile in general. So I would say go as big as possible, but there are, of course, limitations that you have to pay attention to, right? You will have thread pool sizes or like some contentions in your application. So you, as a service owner, probably understand best how high it's possible to go. But you also should consider like a loss of capacity when one of those replicas is down, right? So, yeah? Yes, it's very similar. You can think about maybe Node being a machine, and the replica is a container, like a task.
What you probably balance those between nodes and so on, and you can utilize more CPU on one node, packing more replicas.
Yeah, but you can think about it this way. If a node is a machine, right, we can go only that big, and it has its limitations, right? So this is the first thing. The other is, if you look at this particular machine, it makes sense to have like smaller tasks, and yes, you can pack them up. But when you then look at the total usage, right, in the fleet, you actually are wasting resources because at some point those smaller tasks will cause too much overhead. We actually did those exercises, compared the total resource usage, right? Because we have a lot of other workloads that we can put on those machines. So I will tell you a little bit about it later. Yeah.
Okay. So why bigger tasks are better? For example, very small tasks will get easily overloaded by some stray RPC that uses more resources. This is one of the ways this is problematic. Another is that you waste some memory because you need to pay for the cost of the binary itself with memory, so this is also a cost. The bin packing is a problem, but
we solve it differently.
Yeah.
We have basically, the short version is we have a lot of stuff to pack, so we can pack other things there. Yeah. Okay, so loss of capacity, right? If you have 3 replicas, one is gone, you are losing 30% of capacity. You have to think if your service is ready for it. Also schedulability limits, right? If bin packing gets harder, if your tasks are of size, I don't know, half machine or like bigger than some machines that you have. Okay, and back to Jacek.
So Beata told some about manual limit management. Do you hear me? Okay. 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 Now? Okay. So let's talk about auto scaling. I think I'm losing the. Yeah, it's breaking. Okay, maybe now. Okay, so I'm a member of autopilot team. I'm still working. Okay. Now okay. Okay, now maybe not breaking, okay. So I'm a member of autopilot team. This is the biggest auto-scaling solution we have in internal cloud by adoption. Why do we use auto-scaling? So auto-scaled services have much higher utilization. This is a graph from autopilot paper that we published a couple of years ago. And on the y-axis, you have percentile of service. And on x-axis, you have memory slack. Memory slack is the difference between high percentile of memory usage and the memory limit. And the way to read this graph is that median service that uses autopilot memory scaling has slack that is smaller than 20%, but for non-autopiloted services it's like more than 60%, or it was a couple of years ago. But you might ask that, okay, we just removed all the safety buffers, so obviously the system will use less memory. But maybe the reliability will suffer? And the answer is no. Here we have task percentile. This is if a single service has 1,000 tasks, each of them is calculated separately here. And here is a fraction of free. Oh, I'm sorry. This is fraction of free days. This is percentile of tasks. And the fraction of free days is way higher. Oh, is way higher for autopiloted jobs. But why is this higher? Why can we get good reliability with less safety buffers? This is an example. Sorry for the quality of the plot, but I wanted to show you true plot from actual outage. So this is memory usage plot. This is memory usage actual. This is memory limit the service actually had. And this is recommendation from autopilot that was running in dry mode. So memory usage grew for some reason. Maybe there was a mem leak, maybe some downstream service did something, doesn't matter really. And at 5:30, the system started crashing. It started crashing. So you can see that the replicas die and initialize. And service owner fixed this issue by 8 p.m. So there were 2-hour outage. And automation would have increased the memory limit way earlier. So there will be no outage. So because we can adjust resource limits automatically, the safety buffer needs to provide safety for a lower period of time, so it can be smaller. Okay, so is auto-scaling a solved problem? So maybe it's already done and we don't need to do anything, but it brings some complexity to the system. So for example, first, vocabulary. We have 2 scaling modes. First is vertical. So number of replicas stay the same, but resource limits change. And other is horizontal when we add or remove replicas, but the size of each replica stays the same. So there can be feedback loops which are impossible to in the manually when you adjust limits manually. So for example, some user decides to use all what they quote unquote paid for and fill their whole memory with caches. And what will autoscaling see? Autoscaling will see a service that has very high usage, that's very close to the memory. And I'm tearing again, yes? Oh, yeah. Yeah, we'll switch. Okay. Okay. Is it better? Oh, perfect. So what the automation will see is a service that has very stable memory usage, that's very close to the limit, and it will increase the limit. But increasing the limit will increase the usage. So automation will increase the limit once again. And this can go as long as there is free quota for this service. And how do you solve this? We just tell users not to do this because this is not beneficial to the company. If they have some safety buffers and the safety buffer is free, these resources can be reclaimed and reused, but I will explain how. So this usage pattern is not beneficial to the company, so people should not do this. They should size their caches, for example, using some application-specific metric like hit ratio. But also there is possible very similar feedback loop when there is a service owner that is very, very risk averse. So they cap their memory usage to, let's say, 80% of current limit. And this leads to a negative feedback loop, because what automation sees, it sees very stable memory usage that is below the limit. So it will decrease the limit. And then usage will drop, and automation will keep the limit for some time because it remembers higher usage, but then it will forget. So it will decrease the limit again, and again, and again. So this actually has a business need. So for example, if we have load shedding, this is this technique of dropping RPC requests when this request would overload the application due to memory usage or CPU usage. It will have this usage pattern. So how do we solve that? We integrate it without load shedding, so the integration is safe. And if somebody cannot use the default solution, they just need to provide the signal to auto-scaling that will tell how much resources the service needs. This is rather advanced integration, so only big services should probably use it. But these are not all the feedback loops. We can have two feedback loops, two automation systems fighting one with each other. So one does horizontal scaling, that is adds or remove replicas, and one does vertical scaling, that is sizing each replica up and down. And they both use the same utilization target. They both use the same metric for scaling, utilization target, but the target is different. So for horizontal system, for example, it targets lower utilization than the vertical one. So what happens? First, the vertical system will notice, oh, the utilization is too low for my target, I'll better remove some limits. And then horizontal system, we see, oh, the utilization is too high for my targets, I better add more replicas. And this can go on and go on and go on until the service dies because the tasks are just too small. How do you solve this? If there are two feedback loops, two automation systems, they should use the same target. In other case, the horizontal system should stop looking at the memory limits, because memory limits are something that is transient. It can be changed by the other system. It should use the value that user would provide. It should have some other, should assume capacity of the task to be constant, and then there is no this problem. But this is not only, this is the last feedback loop. So some services have very expensive initialization. So they download some data from somewhere, unpack it, prepare internal memory structures, and these can use 100% of CPU or even more, because we use soft limits. So if there are resources, services can use more CPU than they reserved, and they use it for 30 minutes. So we have service that has this behavior, and it's horizontally scaled, and it uses CPU utilization, and let's assume that right now this service gets a peak of usage, so it's above the utilization target. So horizontal scaling system will add new replicas, which will start initializing, which will increase the average utilization because initialization is very costly. Then average utilization goes up, so the system adds even more replicas which start initializing, and this increases the utilization. This is more initializing replicas, and it dies down only when some replicas stop initializing. So here is an example of actual situation like this. First there was some usage, then there was some spike that led to some higher value of usage due to some reason. But in the meantime, there is this huge usage spike, and this huge usage spike is mainly related due to this initialization cost, and CPU limits went off the charts. How do we solve this problem? We just need to know when the service and the task is ready to serve traffic, and disregard all the CPU samples we get from initializing replicas because they are not indicative of the application performance. Okay, these are all the problems that we can get from any language, but Java has its own own challenges. Some disclaimer, I'm not a Java expert. I have some experience in autoscaling Java, but if you fine-tune JVM parameters, you know way more than me. So feel free to correct or talk to me. I might learn something. So there is also feedback loop that's special to Java. It's very similar to previous one. So early in lifetime of the application, Java virtual machine needs to just-in-time compile the bytecode to a native code, and this process takes more CPU than, so it leads to user spike. But we cannot use the previous trick because the service, the task needs to get real production traffic, so the just-in-time compiler knows what to compile and what are the executed code paths. Another problem is related to memory. So memory automation usually should react to out-of-memory errors. Because if we get out-of-memory errors, it means something is very, very... No, it died? OK. So it means that something is very, very broken, and we need to react quickly. For example, CPU and Go binaries, we can just intercept operating system signal that process was killed due to out of memory, and we push this to autoscaling. For Java, it's more tricky. Java can die in this way. It can happen. But generally, what you get is exhaustion of Java heap size, which is a normal Java exception, which can be intercepted by the application, which could then clear some caches or do something. This could temporarily solve the problem, but also introduce this feedback loop I talked before. But it could be not caught and then cause application to terminate. But applications can terminate for a variety of reasons, and we cannot assume that, we cannot know whether this termination is due to memory or some bug. So there is this very nice flag out of memory error that allows us to export information that this crash is actually due to out of memory. But we might not even get that because Java application can go into GC thrashing state. This is a state when more and more memory is devoted, more and more CPU is devoted to garbage collection, and less CPU is devoted to RPC handling. So what automation sees in this state is it sees a service that uses a lot of CPU, so it will add more CPU, and adding more CPU will make the matters worse because handling traffic uses memory, and with this extra CPU, the service will be able to handle more traffic. Last problem is that Java needs to know maximal heap size, and this is generally a static parameter, which makes scaling harder. And on top of that, not all Java memory usage is in Java heap. So sizing the container requires to size separately heap and non-heap usage because they are not interchangeable. The way we do autoscaling for Java is the safe thing to do is just set XMX as a static value and use autoscaling to right size the non-heap usage. So there is a less of misconfiguration possible. But what we really would like to do is at some point we would like to not have minus XMX and treat Java as every other language. OK, and now back to Beata. Here you go.
Thanks. Just give me a second. Yeah. OK. So Jacek already talked about some challenges related to autoscaling, about feedback loops, but there are also operational challenges. Just give me a second. So basically it's about the fact that you have to treat and think about your service a little bit differently. So first of all, typically a service owner will treat high utilization as my service is at risk signal, right? So to actually catch those times when the outages happen and scale up faster. But in reality, with auto-scaling, high utilization is actually good. Especially with stable memory usage, you are able to really achieve high utilization. So this requires you to think more in terms, oh no, my utilization is large, to, oh no, autoscaler was not able to scale up, right? So you can have your monitoring, for example, on quota, and maybe monitor if autoscaling is doing its work. So, for example, monitor for ohms. Also, it's important that the autoscaling SLOs are really SLOs for the right thing. So if autoscaler promises you that it will be up most times, it's not good enough. If autoscaler promises you that on average services that are autoscaled less, that is also not enough for your service. So the SLOs need to be in terms of what is the overall provisioning safety, what are the conditions to go out of memory, what kind of spikes will be covered. Okay, and now about what we promised you earlier, so about this reclaiming memory and why we don't care that much about bin packing. So we collocate batch and with serving. And you can think it's not really important whether it's batch and serving. You can think about batch as being the lower priority services, jobs, workloads with higher priority. So we then run those lower priority batch services on those resources that are reclaimed from serving workloads. There was actually an exercise, an experiment long time ago, in 2015-ish. And you can see the result on this plot. So on the left, or maybe let's start from the right. So you have on the y-axis, you have number of machines. Then you have the situation where we had separate prod-only load on and separate non-prod load, so this batch and lower priority, right? So if we separated them on machines, we used many more machines than in the case when we actually allow those two types of workloads to run on the same machines. But what happens when actually serving workloads needs the resources that batch already took? So batch can be evicted, it can be throttled, can be killed even, just not too often, of course. And as far as those things don't happen to batch workload too often, there are significant savings here. Of course, we need to be very careful about isolation of those workloads. Okay, another important thing is overcommit. So this is the policy that, yeah?
I'm really sorry.
No?
I have to ask because I'm not sure if we will back to the previous slide.
Yep.
So maybe it was said previously, but how you managed to save all those resources was the real reason that you shared machines when you allowed the, let's say, the left strategy.
The main thing is, it's also related a little bit to overcommit, but basically you can think about it that the resources that the serving jobs do not use right now, right? We allow batch workloads to use. But if the serving workload actually needs them, we then remove the batch if there is no space.
Okay, so it's less idle jobs, less number of the workers or jobs not working.
Yeah, so this is kind of like we are using the limit, the difference between allocation, so the limit, and the actual usage of those serving jobs.
Okay.
Mm-hmm.
Is that where preemptible machines in Google comes from?
Yeah, probably from this idea, exactly. So, like the same people who wrote Borg, then worked on Kubernetes, and there is a lot of those things that actually work for us internally, then we also make available externally. So an overcommit. This is a policy that is enabled for the machines that are serving our internal workloads. So we already saw that on a single machine, there are tasks for multiple jobs, right? For multiple different services. What is the probability that they will all spike at the same time? Those are completely unrelated services, right? So the probability is very low. So we can assume that the capacity of the machine is really some percent greater than it really is, right? And just put there more workloads. When the serving, so those higher priority jobs suddenly want to use all their resources, we need to, as been previously, evict some other workload. But those evictions should happen rarely, so we cannot go crazy with this overcommit factor. So in this graph, you can see, so this is cumulative plots, right? So you can see that without, the black line is sum of machine level peak, and the dotted line is the sum of task level peak. So basically, you can think about that. The dotted line is you add peaks of all the jobs, services that you put on the machine. So this is sum of peaks. And the black line, sum of peaks. And the black line is the sum of peaks, and the, no, wait, yeah. And the dotted line is peak of sum. So basically, oops, sorry, I wanted to use the pointer and I'm going in the wrong direction. Okay, so basically, using overcommit, we are able to get much higher utilization. So you can see that it kind of like achieves maximally like 70%, right? If you use the sum of peaks. Okay, so do we really need autoscaling if we have perfectly working overcommit? Well, those things are related, but very subtly different. So the autoscaling is about making the decision about the specific size of tasks for this service, and overcommit is more about making the usage of machine more efficient. Okay, and back to Jacek again.
Okay, thank you. So now some food for thought. Let's take a few steps back and see the big picture. So the big picture is really, should our service owner be interested in memory and CPU limits? Shouldn't they be just able to tell us, hey, here is my binary, run it well, and maybe alert me when I'm out of budget? So this is the reality we probably would like to have at some point. Of course, limits bring those beautiful isolation guarantees that make sure that no job can hurt the whole Google. So we need to reintroduce that. Okay, and summary, autoscaling decreases cost, decreases toil, and increases reliability. It brings a lot of complexity to the overall system. This is trade-off. It might be worth for you, it might not. For Google, it's very much worth it. And all the discussed projects here are developed in Poland, Warsaw, and Krakow. So thank you. Here are some references to published papers about our internal cluster. And we are open to questions. And if you want to have longer discussion, I'll be hanging out in the booth till 6 p.m. Okay, floor is yours.